Dr. K. Senthilkumar, Assistant Professor, Department of Physics, Loganatha Narayanaswamy Government College, Ponneri, Chennai. He has done PhD in Material Science at Anna University, Chennai. He has 17 years of teaching experience. He has published 5 articles in national and international conferences and journals. He attended more than 14 conferences and workshops in all over India.
Welcome to UGC lecture series. In today's lectures, we are going to see the subject quantum mechanics. Objectives of this session: interpretation of wave function, probability interpretation, then probability current density, condition for physical acceptability of wave function, then linearity and superposition principles. Interpretation of wave function. We know wave function psi, we have seen, that is classically displacement is represented by y, quantum mechanically displacement is represented by psi. So, that wave function psi in the form of x comma t in one dimension, in the form of x, y, z and t in 3 dimensions. Now, we are going to interpret this wave function by means of 2 aspects. One is probability, another one is probability current density. First one is probability interpretation. The wave function psi of r comma t has no physical existence since it can be complex. That means, psi is not a physical variable. So, it is a complex variable, it cannot be measured accurately. Also, it can be taken as a direct measure of the probability at r comma t, since the probability is real and non-negative. However, psi of r comma t must in some way be an index of the presence of the particle at r comma t. A universally accepted statistical interpretation was suggested by Born in 1926 in this regard. He interpreted the product of psi of r comma t and its complex conjugate psi star as the position of probability density p of r comma t. So, that is probability, p refers to probability. So, p of r comma t is equal to psi star of r comma t into psi of r comma t. Already we have seen psi star is the complex conjugate of psi. So, if we multiple complex conjugate with this psi, we get the modulus value. So, modulus of psi of r comma t the square. The quantity modulus of psi of r comma t whole square d tau is then the probability of finding the system at time t in the small volume element d tau surrounding the point r. When this modulus of psi of r comma t the whole square d tau is integrated over the entire space, one should get the total probability, but which is unity. Therefore, integral minus infinity to plus infinity modulus psi of r comma t the whole square d tau is equal to 1. So, from this equation, what we say, this equation is to be finite, that is psi of r comma t must tend to 0 sufficiently as r tends to plus or minus infinity. That means, we integrate this between minus infinity to plus infinity, that represents this equation. We have integrated this from minus infinity to plus infinity. So, that is equal to 1. Hence, one can multiply psi of r comma t by a constant, say n, so that n psi satisfies the condition in the above equation. Then modulus n squared into integral minus infinity to plus infinity modulus of psi of r comma t the whole square d tau is equal to 1. This constant n is called normalization constant, and equation 3 what we have seen here is the normalization condition. Since the Schrodinger wave equation is linear differential equation, n psi is a solution of it. The wave functions for which the integral in equation 2 does not converge will be treated depending on the nature of the functions. Next, we will see the another interpretation in terms of probability content density, that means interpretation of wave function by means of probability current density. The probability of finding a system described by a wave function psi of r comma t in a finite value v in the space given by, that is integral v, this is volume integral psi star psi d tau, and these changes as the wave function evolves in time. To study this, consider the Schrodinger wave equation and its complex conjugate form as under: I h cross dou psi of r comma t by dou t is equal to h cross squared by 2 m del squared plus v of r into psi, that is equation 4. Now, we just take a complex conjugate of this equation 4. So, this psi becomes psi star. So, I h cross dou psi star r comma t by dou t minus h cross squared by 2 m del squared plus v of r into psi star. So, this is equation 5. Here the potential V is assumed to be real, that means potential energy of the particle is assumed to be real. So, multiplying equation 4 by psi star and equation 5 by psi from left hand side and subtracting one another, if we take a difference we get this equation. That means, this equation we have to multiply by psi star, this equation we have to multiply by psi from front side and take a difference of this equation 4 and 5. So, after simplifying we get I h cross psi star dou psi by dou t plus psi into dou psi star by dou t is equal to minus h cross squared by 2 m psi star del squared psi minus psi del squared psi star. This is equation number 6. Then simplifying dou by dou t of psi star psi. So, this is the differentiation of u v. So, we know the u v differentiation u dv plus v du. So, this bracket term we have simplified as dou by dou t of psi star psi, that is equal to I h cross 2 m del dot psi star del psi minus psi del star psi del psi star. This is equation number 7. Now, integrating this equation we get dou by dou t of integral minus infinity to plus infinity psi star psi d tau is equal to I h cross by 2 m integral minus infinity to plus infinity del dot psi star del psi minus psi del psi star d tau. So, I h cross by 2 m into psi star del psi minus psi del psi star between the limits minus infinity to plus infinity. This is equation number 8. If we have a localized wave packet, which is the situation in almost all cases, psi and psi star tends to 0 as r tends to plus or minus infinity. That means, psi and psi star tends to 0 as r tends to plus or minus infinity. That means, if r value is vary from minus infinity to plus infinity and psi star values are 0. So, if we take this aspect in our equation, the right hand side of the equation 8 vanishes. Then we can write dou by dou t of integral minus infinity to plus infinity psi star psi d tau is equal to 0, or dou by dou t of integral minus infinity to plus infinity psi star psi d tau is equal to constant in time. This is equation number 9. By defining a vector j of r comma t called the probability current density. Here the term j of r comma t represents probability current density. So, we can write the equation for current density. J of r comma t is equal to I h cross by 2m psi del psi star minus psi star del psi. This is equation number 10. And substituting in equation 7. So, substituting this concept in equation 7 we get. So, the seventh equation what we have seen, this equation. So, dou p of r comma t by dou t plus del dot j of r comma t is equal to 0. Equation 11 is the equation of continuity for probability, which is analogous to the equation of continuity in hydrodynamics and electrodynamics. With this definition of probability current density, equation 11 becomes a quantum mechanical probability conservation equation. It may be noted that if psi is real, the vector j of r comma t vanishes. Writing the integral form of equation 11 over a finite volume V and using Gauss theorem, we can write, that is, we get the equation dou by dou t of integral V p of r comma t d tau is equal to minus integral V del dot j d tau is equal to closed surface integral. This refers to closed surface integral j dot ds, where S is the area of the enclosed volume V. This result suggests that any decrease in probability in a region is accompanied by an outflow of probability across its surface. In other words, if the probability of finding the system in some region increases with the time, the probability of finding the system outside decreases by the same amount. Next we will see what are the conditions required physically to accept our wave function psi. So, let us see conditions for physical acceptability of wave function. So far we have not raised any questions that what kinds of mathematical functions can serve as wave functions for a particle in quantum mechanics. Actually, the probability interpretation of the wave function makes it necessary that psi should satisfy certain general conditions. The wave function psi must be continuous. All its partial derivatives of the wave function psi must also be continuous. What are the partial derivatives? We know if psi is the wave function, the partial derivatives of this psi is dou psi by dou x, dou psi by dou y, dou psi by dou z. This makes the wave function smooth. The wave function psi must be quadradically integrable. This means that integral psi star psi d tau must exist. Since this integral psi star psi d tau is the probability density, it must be single valued one. The wave functions must form an orthonormal set. Orthonormal means that should be orthogonalized as well as normalized, that we will see here. This means that the wave function must be normalized first, that is integral minus infinity to plus infinity psi I star into psi I d tau is equal to 1, then the wave functions must be orthogonal. So, integral minus infinity to plus infinity psi I star psi j d tau is equal to 0, or integral minus infinity to plus infinity psi I star psi j d tau is equal to delta I j, where delta I j is equal to 1 when I is equal to 0 and delta I j is equal to 0 when I is not equal to j. where this delta ij is called Kronecker delta. The wave function must be finite everywhere. The wave function must satisfy the boundary conditions of the quantum mechanical system. Now, let us see what is meant by normalization. Even before we consider the actual calculation of psi, we can establish certain requirements it must always fulfill. For one thing, since it is proportional to the probability density p of finding the body described by the wave function psi, the integral of overall space must be finite, that is, the body is somewhere after all. If this integral, that is integral minus infinity to plus infinity modulus psi squared dv is equal to 0, that means the particle does not exist and the integral obviously cannot be and still mean anything. Furthermore, this modulus psi squared cannot be negative or complex because of the way it is defined. The only possibility left is that the integral be a finite quantity if psi is to be described properly a real body. It is usually convenient to have modulus psi squared be equal to probability density p of finding the particle described by the wave function psi rather than merely a proportional to p. If this modulus psi squared is equal to p, then it must be true that normalization integral minus infinity to plus infinity modulus psi squared dv is equal to 1. Since if the particle exists somewhere at all times, then integral minus infinity to plus infinity p dv is equal to 1. A wave function that obeys the above equation is said to be normalized. Every acceptable wave function can be normalized by multiplying it by an appropriate constant. That means, what we have seen in this equation is said to be normalized only when multiple that with the constant value. Next, we will see linearity and superposition principles of wave function. So, what we are going to describe in this? So, wave functions can be added, but not probabilities added in the quantum mechanics. An important property of Schrodinger equation is that it is linear in the wave function psi. This is mean that the equation has a terms that psi and its derivatives, but no terms independent of psi, or that involve higher powers of psi or its derivatives. As a result, a linear combination of solutions of Schrodinger equation for a given system is also itself a solution. If psi 1 and psi 2 are the two solutions, that is two wave functions that satisfy the equation, then psi is equal to a1 psi 1 plus a2 psi 2 is also a solution where a1 and a2 are constants. Thus, the wave functions psi 1 and psi 2 obey the superposition principle that other waves do, and we conclude that interference effects can occur for wave functions just as they can for light, sound, water and electromagnetic waves. We know, we have seen in the preceding sections Young's double slit experiments. So, superposition of two or more wave trains becomes interference. So, similarly these wave functions also interfere with each other. So, this diagram shows superposition principle. This is also like Young's double slit experiment with the electrons. So, slit 1 and slit 2. So, these two are simply openings. If it comes only through S1, we have a probability. This is shown by the figure B. So, modulus psi 1 square. Then if it is from slit 2, then we have modulus psi 2 square. So, this is the probability. Then if it comes from any one of this, we have got the probability of these two. If it comes from both the slits, the electron comes from both the slit, we have got the interference pattern. So, we have added here the wave functions, but here we have added the amplitudes, that is the probability amplitudes. Now, let us describe this diagram detailedly. Let us apply this superposition principle to the diffraction of an electron beam. Figure A shows a pair of slits through which a parallel beam of monoenergetic electrons pass on their way to a weaving screen. If slit 1 only is open, the result is the intensity variation shown in the figure B we have seen, that corresponds to the probability density, that is P1 is equal to psi 1 star into psi 1, that is equal to modulus psi 1 square. Similarly, if the slit 2 only is open, that is given in a figure C, then corresponding probability density is, so P2 is equal to psi 2 star into psi 2 is equal to modulus psi 2 square. We might suppose that opening both the slits would give an electron intensity variation described by P1 plus P2, that also we have seen in figure D. However, this is not the case, because in quantum mechanics only wave functions can be added, but not the probabilities. Instead of that, the result with both the slits open, this also we have seen in the figure E. The same pattern of alternating maxima and minima that occurs when a beam of monoenergetic light passes through the double slit. So, here if both the slits are open, we have seen alternate maxima and minima left hand side as well as a right hand side. So, in quantum mechanics only wave functions can be added, but not the probabilities, that is given by the superposition principle. The diffraction pattern of this figure E arises from the superposition psi of the wave function psi 1 and psi 2 of the electrons that have passed through slits 1 and 2. So, psi is equal to psi 1 plus psi 2. The probability density at the screen is therefore, so we have seen in the screen, if both slits are open, we have seen alternate maxima and minima in left hand side as well as in the right hand side, that we will see in terms of equations. So, P is equal to modulus psi squared is equal to modulus of psi 1 plus psi 2 squared plus psi 1 star plus psi 2 star into psi 1 plus psi 2, that is equal to, then P is equal to psi 1 star psi 1 plus psi 2 star psi 2 plus psi 1 star psi 1 plus psi 2 star psi 1. So, this is P is equal to P1 plus P2 plus psi 1 star psi 2 plus psi 2 star psi 1, because psi 1 star into psi 1 is modulus psi 1 squared, instead of modulus psi 1 squared we can write P1. Similarly, psi 2 star into psi 2 is modulus psi 2 squared, instead of modulus psi 2 squared we can write P2. So, P is equal to, we have got this equation. The two terms at the right of this equation represent the difference between figure D and E and are responsibilities for the oscillations of the electron intensity at the screen. Next we will see eigenvalues and eigenfunctions. So, in previous session we have seen and we have derived also eigenvalues and eigenfunctions corresponding to time independent Schrodinger wave equations for stationary state problems. Now, we will see eigenvalues and eigenfunctions. If psi is a well behaved function, then an operator may operate on psi in two different ways depending on the nature of wave function psi. The operator operating on function psi may change the function into another function. So, P cap psi is equal to phi. Then the new function phi will be linearly independent of initial function psi. The operator P operating on some function psi may leave the function unchanged, but with a complex or real multiple, that is P cap psi is equal to lambda psi, where lambda may be real or complex number. This P cap represents a unitary vector. In this case, the function psi is a member of class of physically meaningful function called eigenfunction of the operator. The number lambda is called eigenvalue of the operator associated with the eigenfunction psi. The equation 2 what we have seen here is called eigenvalue equation. Next we will see wave function of a free particle. That means that bounded particle and free particle. If it is bounded, the free particle we consider as a electron may be attached with the nucleus. So, there will be binding. If it is free particle, the freely capable of moving in interatomic spaces. So, we consider as a free particle. So, wave function of free particle we are going to see here. The general free particle wave function is of the form psi of x comma t is equal to a e power I 2 pi by lambda minus omega t, that is equal to a e power I k x minus I omega t, because this 2 pi by lambda we know is a propagation vector is equal to k, which is a complex function can be explained in the form, because we know e power x is equal to cos x plus I sin x. Similarly, we can expand this equation. So, psi of x comma t is equal to a cos of k x minus omega t minus I a sin k x minus omega t. Either the real of imaginary part of this function could be appropriate for a given application. In general, one is interested in particles which are free within some kind of boundary, but have boundary conditions set by some kind of potential. The particle in a box problem is the simplest example. The free particle wave function is associated with the precisely known momentum p is equal to h by lambda. So, we have substituted the equation, we have got h cross k. Now, let us come to the conclusions of this session. What are all the topics we have discussed in this session? We have interpreted the wave function psi in two aspects. One is probability, another one is probability current density. Then we have seen what are the conditions required physically to accept by the wave functions. Then we have seen what is linearity and superposition principles involved in the wave function psi. Now, let us discuss the questions involved in this session. What is meant by normalization of wave function? Write the expression for probability of a wave function. Derive probability current density of a wave function. Then list out the condition for physical acceptability of wave function. Then explain the linearity and the superposition principles of wave function. The rest of the topics in this quantum mechanics we will see in the succeeding sessions. Thank you for your kind attention. Thank you.